The hottest secrets don't always need a medium. Let's uncover the power of thermal radiation. This video explores the fundamentals of radiative heat transfer in systems where it plays a primary role. Real-world examples include thermal annealing of metals, efficient space heating systems, blast furnaces for steel production, boiler furnace chambers, thermal shields for fire safety, spacecraft thermal management, and last but not least, concentrated solar thermal power systems. To follow radiation in action, we first need to unpack what it is, where it comes from, and how it interacts with matter. The electromagnetic spectrum spans an enormous range, from gamma rays fractions of a nanometer, to radio waves with wavelengths of many tens of meters. All electromagnetic waves travel at the speed of light, c, in free space. Over 1 billion kilometers per hour, fast enough to reach the moon in just over a second. But in materials, like glass or water, light slows down to a speed less than c. Although its frequency, f, remains constant. Since wave propagation speed, v, equals frequency times wavelength, the wavelength, lambda, is correspondingly shorter in these media. Electromagnetic radiation arises from a variety of physical processes, from antenna oscillations to atomic transitions. In this video, we focus on thermal radiation, which mostly lies in the infrared and visible parts of the spectrum. It's produced by the random thermal motion of charged particles, from lattice vibrations in solids, to molecular collisions in fluids. To understand thermal radiation, we need to look at how accelerating charges emit electromagnetic waves. In solids, thermal energy sets atomic nuclei into vibrational motion around their lattice positions. In conductive materials, delocalized electrons also contribute, thanks to their high thermal agitation and mobility. According to classical electrodynamics, these thermally driven accelerations distort the surrounding electric field. But the disturbance doesn't spread instantly, rather, a kink forms in the field lines and zips outward at the speed of light. That moving disturbance is what we call electromagnetic radiation. And importantly, the electric field, E, comes hand in hand with a magnetic field, B, both in sync, both perpendicular to each other, and to the wave's travel direction. This dynamic between jostling charges and self-sustaining fields is the heart of thermal emission. Atoms bounce and jiggle tight. Their charges spark electromagnetic light. Who knew warmth could be so bright? Having seen how thermal radiation originates, we now turn our attention to what happens when that radiation hits a surface. This interaction lies at the heart of radiative heat transfer. When electromagnetic radiation strikes a material, it can be reflected, absorbed, or transmitted. Reflection sends energy back into the environment, absorption transfers energy into the material, often in the form of internal energy, and transmission allows radiation to pass through. But for most solid materials, especially metals and dense ceramics, transmission is negligible. These materials are effectively opaque at thermal wavelengths. So, understanding how reflection and absorption depend on surface properties and wavelength is key to predicting radiative behavior. To design systems that manage thermal radiation effectively, we need to understand how surfaces interact with different wavelengths. Material choice, surface finish, and temperature all shape how radiation is absorbed, reflected, or emitted. Wavelength plays a central role in how radiation interacts with matter, determining how materials reflect, absorb, and transmit energy. In the visible range, absorption is mainly driven by electronic transitions. Materials absorb specific wavelengths that match the energy gaps between electron states, while the remaining light is reflected or transmitted. This selective absorption shapes both the surface's visual appearance and its thermal behavior. Consider a painted surface. Pigment molecules absorb parts of the incident white light depending on their electronic structure. In red paint, for instance, red wavelengths are not absorbed, they enter the pigment layer, scatter within it, and re-emerge as diffuse reflection, which gives the surface its color. At the same time, some of the light that doesn't enter the layer is reflected directly, preserving its angle and intensity. This is specular reflection, which contributes to the surface's glossy appearance. Let's now examine a red-painted ball at 20 degrees Celsius, representative of ambient conditions. The red appearance of the ball arises because it selectively reflects light strongly around a wavelength of 623 nanometers. We can represent this using a spectral plot. A spectrum, in general, shows how the energy of radiation is distributed across different wavelengths. On this plot, we place spectral emission, 𝐸𝑏, on the vertical axis, and wavelength, 𝝺, on the horizontal. Here, 𝐸𝑏 represents the total radiative power emitted per square meter per unit wavelength, summed over all angles, typical of diffuse emission. For our red-painted ball, most of the reflected light is concentrated in a narrow band around 623 nanometers, or 0.623 microns. That peak in the visible red range is what gives the surface its distinctive color to the human eye. Let's consider the same ball, but magically transform it from 20 to 800 degrees Celsius. Now, it is glowing red hot, with a similar color to the original painted ball. Looks similar, but what's the difference here? Shifting attention from reflection to thermal emission, we now capture a wider spectrum of wavelengths. At 800 degrees Celsius, the ball no longer just reflects red light, it now glows red due to thermal emission. Thermal emission is everywhere, occurring for all objects with a temperature above absolute zero. A material's appearance can hint at how it behaves thermally, since reflection and emission depend on how surfaces interact with different wavelengths. An idealized reference is referred to as a blackbody. A blackbody absorbs all incident radiation and emits thermal radiation diffusely, that is, isotropic in all directions, with a spectral distribution that depends only on its temperature. For a red object at room temperature, the observed spectrum is dominated by selective reflection of ambient light, particularly in the red region. When the same object is heated to 800 degrees Celsius, its thermal emission spectrum shifts so that part of the emitted radiation enters the visible range, overlapping with the red wavelengths previously seen due to reflection. The term red hot here refers to this condition, when the object's own thermal radiation begins to emit visibly in the red portion of the spectrum. The spectral distribution you see here represents thermal emission from a blackbody. A glowing steel ball at around 800 Celsius, or 1100 Kelvin, behaves very much like one. While its red glow is clearly visible, that's just a small fraction of the total radiation it emits. In fact, most of the emission lies within the infrared. We can conceptually divide the total spectrum into two bands, the visible and the infrared. This entire spectral shape is described by Planck's law. It gives the power emitted per unit wavelength, and it introduces two fundamental physical constants, Planck's constant, h, relating energy to frequency, and Boltzmann's constant, k, connecting energy to temperature. The two spectral bands we've just discussed, visible and infrared, can each be captured using different imaging systems. A standard camera detects the visible spectrum, much like our eyes, revealing the familiar appearance of objects. In contrast, a thermographic infrared camera detects thermal radiation in the infrared band. This allows us to visualize heat patterns that are otherwise invisible. This method, called thermographic IR imaging, is used extensively in engineering, diagnostics, and monitoring, anywhere surface temperature mapping is important. Thermal radiation is a universal feature of both natural and engineered systems. It spans a broad spectral range, from the visible region into the far infrared. While some of this radiation can be seen, much of it lies beyond the sensitivity of the human eye. So far, we have referred to the concept of a blackbody, but what exactly is it? First, let's think in terms of analogies. The term blackbody is a bit misleading, like calling a microwave a beepy food spinner just because it has a turntable. The name blackbody reflects what it looks like when it's cold and absorbing light, not what it fundamentally does. In reality, a blackbody is defined by how it emits radiation, not by its color or appearance. Instead, imagine a sponge that instantly soaks up water, then wrings itself out just as efficiently. That's what a blackbody does, but with radiation. It's the perfect sponge for light, absorbing every wavelength that hits it without a trace of reflection. But the more it takes in, the more it glows, emitting radiation solely based on its temperature. Another way to think about a blackbody is to frame it as a rate process, much like conduction. We described conduction as a rate process in our earlier video, Fundamentals of Heat Transfer. Let's briefly recall that. In conduction, rate of heat flow is driven by a temperature difference. The resistance to heat flow is inversely related to the material's thermal conductivity. As we reduce the resistance by increasing conductivity, the rate of heat flow increases. At the extreme, we reach a lower bound for resistance, which is achieved with a material like diamond, known for its exceptionally high thermal conductivity. Now, let's consider thermal radiation in a similar framework. Here, the driving force is the thermal agitation of charges within the material. Resistance, here, refers to inefficiencies in converting thermal motion into outward radiation. This arises from internal screening or attenuation, limiting how much radiation escapes the surface. A real material's emission spectrum is shown here by the green curve, which reflects these limitations. Radiative emission increases as resistance drops, with the dial moving right and the purple range contracting. Eventually, we hit a fundamental thermodynamic maximum, the Blackbody limit. At this point, we reach the maximum possible spectral emission for a given temperature, shown here by the red curve. This red curve outlines the Blackbody limit, an idealized case where no radiation is internally attenuated, and all thermal agitation contributes fully to emission. So, how do we use spectrally resolved emission to understand and quantify radiative heat transfer? One of the key goals here is to figure out how much thermal radiation is exchanged between surfaces. Our first step is to compute the Blackbody surface emissive power, 𝐸𝑏, which represents the theoretical maximum total emission. With this next step, we'll start to make sense of it. Let's explore. Welcome back. What we've just seen from integrating Planck's distribution across all wavelengths leads us to a powerful result, the Stefan-Boltzmann law. This law tells us that the total emissive power per square meter of a perfect blackbody is proportional to the fourth power of temperature. That's a very steep increase. Even a small rise in temperature leads to a dramatic jump in emitted radiation. This makes it one of the most important thermal power laws in physics and engineering. But remember, it only applies to ideal blackbodies. For real materials, we'll need to account for emissivity, which we'll explore shortly. Now that we've integrated Planck's distribution to get a clean result for heat flow based solely on temperature, it might seem like we're done with spectral details. But this only applies to an ideal blackbody. For real surfaces, spectral information continues to matter. Let's now revisit Planck's blackbody spectrum and see how it evolves with temperature. As temperature increases, the curve becomes taller and narrower, with the total integrated emission rising, in line with the Stefan, Boltzmann law seen earlier. At the same time, the peak shifts to shorter wavelengths. This is Wien's displacement law in action. The peak wavelength is inversely proportional to temperature. This blue shift means hotter objects radiate more in the visible and even ultraviolet range. In engineering, this behavior isn't just academic, we can even use it diagnostically to estimate temperature. If a surface's emission spectrum doesn't follow this pattern, it's not behaving as a blackbody. That signals the need to account for spectral emissivity, especially for real materials like oxidized metals, ceramics, or coated surfaces. Real surfaces don't emit as much radiation as blackbodies, a point we introduced earlier in this video when discussing the blackbody limit, and they also don't follow the same spectral profile. Their behavior is governed by spectral emissivity, epsilon lambda, a function that depends on both wavelength and temperature. Its value ranges between 0 and 1, scaling the blackbody emission accordingly, with a perfect blackbody having epsilon equals 1. So instead of a smooth Planck distribution, real surfaces exhibit jagged, irregular spectra. To determine the actual emission at any wavelength, we multiply the blackbody spectral intensity, E lambda, by the emissivity, epsilon lambda. This gives each material a distinct spectral signature, which must be accounted for when modeling radiative heat transfer from real surfaces. In the ideal case, radiative heat exchange between two black surfaces depends solely on their temperatures, as given by the Stefan, Boltzmann law. However, real surfaces emit less than a blackbody, so a correction is needed. For the common example of two large parallel opaque plates with diffuse surfaces, the net radiative heat flux per unit area is adjusted to account for surface emissivities. The resulting expression includes both emissivities in the denominator and arises from standard radiative analysis, not detailed here. This corrected form prevents overestimating the heat transfer by properly accounting for the fact that real materials are neither perfect emitters or absorbers. Since real surfaces don't emit uniformly across wavelengths, working with spectral emissivity can get complicated. To simplify things, we define an average emissivity, epsilon of t. It tells us how much energy the surface emits compared to a perfect blackbody at the same temperature. Mathematically, it's the ratio of two integrals, the surface's actual spectrum over all wavelengths, divided by the blackbody spectrum. This averaged value still depends on temperature and is shaped by the material's properties, surface finish, and even oxidation state. So, to wrap up, thermal radiation originates from the random motion of charges inside materials, producing electromagnetic waves that carry energy away. We saw how this process depends on temperature and surface properties, with blackbodies serving as the ideal reference. Real surfaces emit less, so we adjust using emissivity. By integrating spectral information through Planck's law, we arrived at powerful tools like the Stefan-Boltzmann equation to model net heat flow. These principles are crucial wherever radiation dominates, from industrial furnaces to satellites. A solid grasp of radiative heat transfer helps engineers design more efficient, safer, and thermally optimized systems. One last thing, before we go, let's take a moment to unpack what may seem like a contradiction. Here's a bit of context. At a given temperature, materials can exhibit vastly different thermal emission profiles. Take chromium for example, it's a metal, unlike most metals, it has a low emissivity. Its emission is significantly suppressed. In contrast, charcoal behaves almost like a perfect blackbody. Its emission spectrum closely matches the theoretical blackbody limit, giving it an average emissivity just below 1. Now, let's consider two more materials, aluminium oxide and black anodized aluminium. Which one do you think behaves more like a blackbody? Here's a hint: consider how the material's internal structure governs both its spectral and average emissivity. Subtle changes at the micro level can have a profound effect on how radiation is emitted. We'd love to hear your thoughts in the comments. If you enjoyed this video, you may want to check out the following covering similar themes. Thank you for watching. Take care, bye for now.